Okay, so Vladimir Voevodsky, simplicial and cubical part 2.
Part 2, coherent nerve or cubical category. So let me first remind the main context of the last lecture, which was that I outlined a construction of our two functors okay, so first maybe so the cube category here will be the category with objects, natural numbers, and morphisms from M to N being given by monotone functions from the partially ordered set 0 less than 1 to the power m to the partially ordered set 0 less than 1 to the power m. This category, as we observed, has a structure of a Laver's theory corresponding, which can be represented as a structure of bounded distributive lattices. So we say the category of cubical sets is the category of functors from the contravariant functors, or just functors from the opposite to the category of cubes to the category of sets. Similarly to how the category of simplicial sets is the category of contravariant functors from the simplicial category to the category of sets. And we have constructed two functors C set to S set and U from S set to C set, and an adjunction where T is a left adjoint to U, and we showed that and we've also constructed a topology constructed delta topology on the category of cubes such that U is an equivalence to the subcategory of delta shifts. So simplicial sets are shifts in the delta topology on the category of cubes, while cubical sets are pre-shifts on the same category. And of course then T is the functor of associated shift. and we discussed various things related to it. So, right. So let me. So today we want to consider the categories of C cat and S cat of small cubical categories and small simplicial categories. There is a well-known construction which is very widely used by Lurie in particular, but which goes back. I'm sorry, I don't know who the original author is, of something called coherent nerve, which is a functor from the category of simplicial categories into the category of simplicial sets. And we are going to describe and discuss something called simplicial nerve, for the lack of better term, from cubical categories to the category of simplicial sets, and the relationship between the two. So let's first just make sure that we understand the concepts in the same time, or in the same way. A cubical category, for example, is a category enriched over the category of cubical sets. So it's cubical category is a contraption where one has C, which is a set, and then for all x, y in of C, one has more x, y, which is now a cubical set. And our composition is given by the x, y, z in of C. We have a composition which uses the product structure on the category of cubical sets. So this product structure will have to be chosen before we can, if we're doing things carefully, then we first have to say, let's construct a binary product structure, and then we can say what the cubical category is. So if one starts writing down the associativity axiom, then one will discover that I just want to emphasize it, because it's something which becomes more pronounced as one tries to do something like higher category theory. So if I'll just denote morphisms like this, without writing the word more, then I'll have x, y, y, z, z, t, and from here I can go to x, y, y, t, and to x, t. But I cannot go from here to x, z, z, t. So I need to actually use the associativity of the product as an arrow in one of the directions. And then I can say x, z, t going here, and this should commute. So that's the associativity condition. And of course, the same works. The same kind of thing needs to be taken care of in the simplicial case. So we have the notion of a simplicial functor and cubical functor. So these are functors where morphisms are where one uses a morphism between simplicial or cubical sets instead of morphism function between the corresponding sets of morphisms. And one can verify and get these categories C cat and S cat. Now there is a comment here which I want to make because we are in such a cameral environment. So there is a problem in trying to define a category of, let's say, simplicial categories or cubical categories in univalent foundations. Just as there is a problem in defining a category of categories in univalent foundations, because the collection of categories does not because the collection of functors between two categories does not form a set. So and this leads to a whole bunch of difficulties later on. For example, it's not possible to immediately define what a nerve of a category is in unimass, for example. Because when I define a nerve of a category, it's a simplicial set whose set of vertices is the set of objects of the category, but the collection of objects of the category is not a set. So so I get a difficulty, and it's not very clear what is the best way of solving it, and it propagates further, especially in the type theory, because the construction of universes are going back to Thomas Stryker in topos in toposes of free shifts doesn't work, and many other things don't work because of this particular issue, and it's becoming more and more annoying as we move forward.
Don't move forward, yes.
Huh?
Well, as you don't move forward, as it were.
I don't mean move forward in my talk. I mean move forward in general in we cannot properly formalize our cubical model because of that. So that's an open problem, which a good solution for which would be very welcome. Maybe one can define somehow simplicial sets, which are not exactly a set, but it's only x0 which is not a set, and everything else is a set over this non-set. So the morphisms are sets, so it's kind of simplicial almost set. I don't know. So since we have these two functors, c and u, both of these functors commute with finite products and preserve the final object. So they can be both used to define similar functors between the categories of cubical and simplicial categories. So the current notation is this, which is probably not the best notation. So to get from a C cat to S cat, we apply C to all the morphism, to all the cubical sets of morphisms. To get from U from simplicial category to cubical category, we apply U to all the simplicial sets of morphisms. One can verify that the junction between those two can be used to construct an adjunction here also. So, as I said, we're going to establish, to construct this n delta and to establish a connection between n delta and n COH. And the connection going to be as follows. So now I can formulate the theorem, which says that n coh of C, so C here is a simplicial category, is constructively isomorphic to which one is this? To n delta of U of C. So the cool thing here is that we decompose the coherent nerve into two functors, each of them being more simple than their composition. And in fact, it is this functor which corresponds to somehow intuitive picture of what should be should be happening, and it's clear that to get a coherent nerve, one really adds this kind of triangulation to it. So so we have examples. So the category of cubical sets can be easily made extended to a cubical category, and we'll treat it as a cubical category. Can be given structure of cubical category, and it plays a special role in this theory as one develops it further. It's similar to the category of simplicial sets being a simplicial category. So let's now get to the construction. And so the idea is one usually constructs functors to, often constructs functors to simplicial sets, is to, we want to construct a cosimplicial object in the category of cubical categories, which, again, for the lack of better name, we'll be calling C Gothic, or well, I was taught just a couple of weeks ago how to display the Gothic letters on the blackboard. So you bring in
the whole alphabet
the
for us?
talk.
Can you do the whole alphabet for us?
No, I was only showed C.
You're going to start somewhere.
Fair
enough. So we want to construct a functor. So in order to do this, one has to provide a number of constructions and then prove a number of their properties. So first, for all n in NAT, which is the set of objects of delta, to construct a cubical category in here. So this splits into a sequence of subproblems. So we set of En equals 0, n, so the standard set with n plus 1 elements. So I need to define a cubical set for each pair ij between 0 and n. I need to define a cubical set. So so we define it as follows: is g minus I minus 1. So, sorry, maybe I should write it like this. So this is the unida of g minus I minus 1. It's a cube of dimension g minus I minus 1. If g minus I minus 1 greater or equal to 0, is there union? I don't know. Well, I'll write this Tn1. So the standard set was one element. If g minus I minus 1 equals minus 1, and empty if g minus I minus 1 is less or equal to minus 2. Now it looks a little peculiar. We can make this comment now, or we can make it later. The category which I'm going to construct this cubical category is in fact a cubical category which is obtained by freely adding unions to a non-unital cubical category where morphisms from I to I are equivalent to set. So that's so this is STN1. This is the union, and because it's morphisms from I to I, and it should contain union, and so that's the union. And if we don't include unions in our axiomatics, if we consider non-unital categories, then we can see that they're empty for j minus I minus 1 less or equal to minus 1, and then we add unions freely. Now, to define composition, for composition, let's introduce the following intuitive notation. So we need to define more ij, more jk, more ik. Now this is a cube and this is a cube. So this is a product of two cubes. And the product of two cubes is equivalent, is naturally, and we are given a standard isomorphism between the product of two cubes and a cube. And this is again a cube. So I need to construct a morphism from one cube to another cube. And because the Unetta functor is a full embedding, it's the same as constructing morphisms from one cube to another cube in the cube category. So this set of morphisms is bijective with monotone functions from 0 less than 1, and here I'll have I plus j minus 1 plus what did I say here? Did I say it? Yeah. Okay. J minus I minus 1 plus k minus j minus 1 into 0 less than 1 k minus I minus 1. So this is actually equal to k minus I minus 2. So I have k minus I minus 2 elements from this set, and I need to create one more element and somehow to so it is convenient to think of and I'm unfortunately here I haven't yet created a little narrative to make it strictly kind of very, very carefully constructed how to think, which would include all the isomorphisms hidden here. But it's convenient to think of this as one-dimensional cube, kind of to the power going from I plus 1 j minus 1. I plus 1 j minus 1. So one needs to put some little narrative around. So then what I have here is I have an element from here, which is so then here instead of this abstract sum, I'll have this interval joined with the interval which starts in the same point and then continues to k minus 1. And what I'm going to do is to take x I plus 1 x j minus 1 1 x j plus 1 x j minus 1. It is a monotone map. Yeah. And when it's written in this form, then it becomes very easy to at least convince oneself that certain properties hold. And for example, we can verify associative sequence. So that gave me composition. And for associativity, I have x times y times z equals x times y 1z equals x 1 y 1z equals x.
Yeah, okay. Okay. Fair enough.
But that's actually easy to make into a proof. If I start writing indices directly, then it will be this one good example where a lot of computations with truncated minus are needed. So this gives us. So far it gave us this category Cn, cubical category. Now the next problem we have is to construct, so for all phi m to n in delta, to construct let me denote it phi over star just for the notational convenience from C m to C n. And that should be a cubical function.
Don't you mean in cube?
No. It's a functor from delta.
It's a function from delta, all right. Right.
Because we want to obtain a simplicial set.
Yeah, okay.
And so it's a functor from delta. So that fits again in the common theme or relationship between cubical and simplicial. Now at the level of categories. So we do the following. We say phi over star of equals phi. Because the objects are exactly numbers from 0 to n plus 1 and 0 to n plus 1. Now I need for ij in Span in M, where M is understood as a standard finite set with m plus 1 element, to construct more C M I J into more C N phi of I phi of J. I'll write a formula, so I'm following that example of some of our best colleagues working with cubical sets, who are writing formulas instead of explaining what they mean. Well, I'll try to explain what it means also. So this is this this cube, and that is that cube. So it's again the question of making a cube into a cube. So again, building a morphism in the cube category itself, and we'll do x I plus 1 x j minus 1 maps to x bar I plus 1 x bar y j minus 1 where x bar s equals max sorry, x bar c max x s s in I minus 1 now it turns out that verifying that the composition axiom is easy. It corresponds to the fact that computing maximum of a finite set or its partition is the same thing, or the maximum of maxima of its partitions is the same thing. But however, all of that it needs to be verified, and so one has to now one has to verify several properties, and at the end one comes to the proposition that this data describes a function now let's draw some pictures. Let's see what, so now since I have this functor, I can define my simplicial nerve functor now, I mentioned this theorem back there, which said that if I compose it with U, then I get exactly the usual coherent nerve functor. I'm not going to give a proof of this theorem because that would require me to go all the way back in a sense and remind the detailed definition of what is a coherent nerve functor. In fact, if one looks at this definition, one discovers that it basically is the composition of, of this triangulation with what we described. And I'll draw some pictures which will, I mean, at least in my head, this construction it existed way before the coherent nerve functor was defined, except I didn't know what a cubical set is, and but I knew what is happening there for small n. And I always knew that what comes up are cubes. But we didn't have anybody interested in cubes. So so here is a picture. So n delta C0 is just of C as one group. N delta, because this category of 0 is just a one-point category. C1 is just more C in a sense. It's a union of over xy in of C more xy 0. Again, so as one, the same as for whether it's cubical or simplicial, in dimension 0, 1, there is no difference, and things are coincide. Now, actually, I think even in dimension 2 there is no difference, probably. So let's have a look at what this is. So an element here is a functor from C2 to C. Now this gadget is a cubical category which has three objects, 0, 1, 2. Now it has kind of it's one morphisms are generated by this one, but the composition of these two is not equal to this. Instead, there is a homotopy, so a one-dimensional cube, which goes from this element in morphisms from 0 to 2 to the composition of these two in morphisms from 0 to 2. And the direction is somehow fixed by by the construction. So the first interesting thing happens next. I think it's still exactly the same as in coherent. So one can draw this category a little informally, and looks as follows. Wait, what am I? So these are one morphisms, but now the triangles are not strictly commutative. Each triangle is of this form. So now if I start looking from here to here, so this is 0, 3, and here I should get a square. In my definition, it will j minus I minus 1 will be 3 minus 0 minus 1, which is 2. So I should get a square somehow. And this square corresponds to the four sides of this three-dimensional simplex. Each side, in fact, it's a square like this, where each side corresponds to one of the faces of the simplex. and it has to be composed sometimes to get to the same cubical set of morphisms. So one can write this explicitly what the sides are, but this is the picture, and this is the picture as we know it. So so it's this and this correspond to one side, and the two in the back correspond to another side. And the whole thing gives a square. Now, when one goes one dimension higher, so if I go from 0, 1, 2, 3, 4, will be a 4-dimensional simplex, which is a little difficult to draw. But note that the 4-dimensional simplex has 5 sides, while 3-dimensional cube has 6 sides. So one can wonder, so what happens? What happens is that it will be a cube, of course. 5 of its sides will correspond to codimension 1 faces of the 5-dimensional simplex, and one extra side will correspond to it's the first time when I have this picture. In the 4-dimension simplex, I have two-dimensional simplexes attached to each other by a point. And so this simplex provides me with a 1-dimensional cube, and this simplex provides me with a 1-dimensional cube. So when I compose the two, I acquire a 2-dimensional square, which is a product of two 1-dimensionals, but still it's a square. And this is the 6th side of the cube. And if you start looking at in the next dimension, you'll see exactly the same thing. So there will be n+1 sides corresponding to the kind of irreducible the cases of a face of codimension 1, and then there will be more and more sides corresponding to various kind of reducible chains of simplices in the inside the big simplex. So it's very natural. And in fact, when one builds a theory of 2 categories, or bicategories, how we would call it today, one sometimes doesn't even want to say that this equals this. I mean, that this is isomorphic this, right? Sometimes one may want to say that there is a morphism going, a two-morphism going in one direction. And if it's a two-morphism going in one direction, then splitting it into 2 triangles doesn't work very well, because splitting it into 2 triangles is what the coherent nerve of a simplicial category does. So this is the coherent nerve, and it goes from cubical to simplicial, and we can apply it to many interesting categories now, because for example, the category of contexts in the cubical type theory is a cubical category, and moreover, I'll show you something a little more. I have a few more minutes, and I'll be very So so we can define and I'm not going to write down the definition. It's a classical definition. If there exists a filling of both open boxes and the 0 and the 1. And I also want to add here X is universally can if for all k x to the k, the function cubical set is can. And here is a question. Give an example of a can non-universally can cubical set, and I know that Chris have thought about it for a while and said that it's becomes somehow very involved, and he doesn't know. So far we don't know of any examples. I mean, but we expect them to exist. I also can say that in a simple lemma that for a can X in simplicial sets, which direction this functors go. Well, let's say U. U of X is universally can cubical set. So one cannot build examples of non-universally can from simplicial sets.
But what happens in simplicial sets? I mean, if something, is there a difference between being can and universally can in
Yeah,
simplicial?
in simplicial sets, everything is universally can. But somehow we don't expect it here. So again, definition. Cubical category is locally can if all the morphism cubical sets are can. And here is the theorem. If C is locally can, then the simplicial nerve of C is a quasi-category. So not only again, if we take the category of contexts of cubical type theory, there everything, as far as I understand, is can, and that means that its simplicial nerve is a quasi-category. So we obtain a quasi-category which may be a very kind of short way of connecting homotopy type theory to the theory of quasi-categories. That which Chris originally was doing in a very sophisticated way using this Hammock localizations, I think, some version of that in his thesis, to somehow get from a model of Martin-Lev identity types to quasi-categories and to relate their properties. So here it seems one can get from a cubical type theory, one doesn't need to add any Martin-Lev identity types. One only needs the operation which makes things can, nothing else, and one gets a quasi-category. Then we can add, for example, dependent products, and then we can ask whether this quasi-category is locally Cartesianly closed quasi-category. But it seems like the connection becomes much more explicit. I mean, it's computable. And so let's say theorem 2, theorem 3, if C is locally Kan and all morphisms are equivalences, it's easy to define what it means for a morphism to be an equivalence. It means that there exists a morphism in the opposite direction, such that both compositions are homotopic to identities, where homotopy should go through a zigzag, but in the Kan case, it can just go through one cube. So if C is locally Kan and all morphisms are equivalences, then nerve delta C is Kan. So again, here we can say, let's consider Kan cubical set, universal Kan cubical sets, and their equivalences. We'll get a locally Kan cubical category where all morphisms are equivalences. Let's take its simplicial nerve. We'll get something which will look very much like a universe. Moreover, but now this is I'm finishing my second talk, but there is actually a third part. Which is about a certain canonical fibration, which exists over n delta of the category of cubical sets. And using this canonical fibration, it's a simplicial fibration, which is actually gives another connection between cubical and simplicial, because the vertices of this thing will be will correspond to cubical sets. And if I have a simplicial fibration over it, then I have a simplicial set sticking over every cubical set. And one can draw them in simple cases, and it's peculiar. I don't know, for example, whether it's to what extent it's functorial but one can use this fibration, which has very constructive, very explicit description to give an alternative description of something in Lurie's work, which is called straightening unstraightening. And according to Chris Kapulkin, who is familiar with that activity, that was always a very mysterious part of Lurie's kind of toolbox, which he used in many important places, but nobody could ever understand what it is. So here it actually comes in a very, very natural way. Again, one draws similar pictures, and then one generalizes from these pictures and gets explicit formulas. So, so that's our work, which we have been doing for I mean, which has been written almost for 2 years, but I complain that the proofs are not detailed enough for me to put it on the archive. but I don't know, maybe now. And I don't know, there are some computations I would like to. Yes, and I want to make one more comment which I forgot, which is interesting. So to construct this category, this Cn. So these compositions, the formula for compositions just involved putting 1 in between. So it really didn't, you really didn't need anything other than what was it? A phase. So one can argue, so let's just take phases and just leave phases in the structure, and then we can still build things. It turns out to be more interesting than that, because when you start looking at the construction of the functor, I mean the map from natural numbers to CCAT, you only need phases. But when you want to have a functor for each simplicial morphism, it turns out that what you need are straight degeneracies, phases, and one of the connections. I mean, you don't need this. You're free to choose which one you like. So these 3 things are necessary. You don't need permutations. You don't need diagonals, or whatever else there might be. But these 3 things are necessary. But that's the only part of the structure which appears in this whole application.
Does the functor n delta, does it have any exactness properties?
Well, n delta, because it's obtained by morphisms from something, it commutes with finite. It commutes with limits.
Yes.
So it commutes with limits. It doesn't have anything. I cannot say anything good about colimits. It has an adjoint. Wait. Right. It has a left adjoint. It has a left adjoint, which is the left Kahn extension of this functor C along the net embedding. And this gives a functor from simplicial sets to cubical categories. So there is the concept of a cubical category freely generated by a simplicial set.
That's quite. It's not very explicit exactly what that is, just by saying that, is it?
Well, we know what it is for simplices.
Yes, sure.
So now if you start gluing them together,
I'm just thinking, I mean, is there some way of describing what this is in more abstract terms, in terms of, you know, you've got the cube category is what it's the classifier for flat distributive lattices or something.
Yeah.
Simplicial sets is the classifier for, you know, non-trivial intervals. Yeah. So is there some way of a cheap way, as it were, of getting this in those terms?
I don't know. There well might be. But I would rather look for just C itself.
I mean, obviously, if you're going to do calculations, you need.
But I mean, to try to somehow maybe to have some abstract characterization of this cubical categories. Maybe they are remarkable in some way.
I mean, it's certainly possible, but you've got to somehow in this combinatorics, something kind of completely new to me is going on, even if you've seen it for years and years and years.
Well, I knew it back when Prof and I were working on this multi-categories in late 80s.
When you shove a 1 in, could you have shoved a 0 in, or does it has to be 1?
Yes, it's you can
You
choose.
could do
You
that.
have to choose one. I mean, you have to choose 0 or 1.
Yes.
Uh,
I see. Then you stick to that, and then.
and stick to that. Yes.
I mean, this combinatorics, I mean, it comes up in other places, or I mean, it seems as if it must be terribly fundamental because it's.
Well, we actually so there is a paper by Kapranov and myself, which is called free and category generated by a cube and high-brew orders.
Right. Yes. Right.
And there is a discussion of it there. There is some kind of a concept of a derived pasting scheme. If I have a pasting diagram, and so it has 0 and it has 1, so it has beginning and it has end. So I may consider all the paths from beginning to end. And I can try to build a new pasting diagram where the vertices will be this path. So in the case of a simplex, one recovers in the case of a simplex, one recovers the stash of polygons.
Right.
However, this wait, am I saying the right thing here? No, I think in the case of a simplex, one recovers a cube. In the case of a okay, in the case of a simplex, one recovers well, let's count. So here is a three-dimensional thing. So how many pass from 0 to 3 other? So there is the shortest one. There are 2 passes of length 2, and there is 1 pass of length 3. So there are 4. So one recovers a square. If one looks at the next dimension, I think it's exactly the subsets in the set of from 0 to n. Because it, how you travel there. So you have to the n, which recovers the cube. If you do it for a cube, you recover something which is called permutahedron. And then you can try to do it for a permutahedron, but there are some problems. I mean, the construction which we had, I think, didn't want to work already for the next step, and it was using the convex geometry, some reasoning from convex geometry. But in general, it seems like maybe one can do it in a combinatorial way, but it's not going to be a convex polygon anymore. So there is this derived derived passing schemes. And so this passage from simplex to cube is the derived passing scheme. And that's precisely the geometry which goes on here.
Okay.
Thank you very much.